Hello there. This video recaps Ekman Motion, focusing mainly on the mathematical derivations of the key features of Ekman Motion, these being the Ekman spiral and Ekman transport. The wind carries momentum due to its motion. The roughness of the ocean's surface causes friction between the moving air and water, creating a force at the water's surface. The force from the wind is not evenly distributed, but acts over the surface area of the ocean. So we have a shear stress, defined as a tangential force per unit area acting parallel to the ocean's surface. Wind stress is, as I said, a force parallel to the ocean's surface, causing the uppermost layer of the ocean to move in the same direction as the wind. And this top layer exerts a shear stress on the layer beneath it, which in turn exerts a shear stress on the layer below that, and so on. The stress between the layers is proportional to the rate of velocity change between them, which is dictated by the fluid's viscosity. We can visualize a slab of ocean fluid moving in the x direction with thickness delta z. To understand how forces act within the ocean, we begin by calculating the net force per unit area in the x direction. This force is derived from the difference in shear stress between the top, z plus delta z, and the bottom, z. Next, we consider the mass per unit area of the fluid slab. This is represented as the product of the fluid density, denoted by ρ, and the slab thickness, delta z. To calculate the acceleration of this fluid slab, we divide the net force per unit area in the x direction by the mass per unit area. This gives us the term F sub x over m, which represents the acceleration per unit mass in the x direction. Substituting the definitions in, we get the acceleration per unit mass being directly proportional to the vertical gradient of shear stress, scaled by the fluid's density. This also applies in the y direction, hence we have an expression for horizontal force. Then substituting in the shear stress equation from earlier and kinematic viscosity, we can represent horizontal acceleration per unit mass in terms of horizontal velocity. Now remember the thermal wind equations. These arise when the Coriolis force balances the pressure gradient force. If in our scenario we suppose that motion occurs only in the horizontal, then instead of a balance between the Coriolis and pressure gradient forces, we now assume the Coriolis force is balanced by viscous forces. To simplify the maths, we introduce S, which represents the velocity as a complex number, a 2D vector where u is the real part and v is the imaginary part. Multiplying the second of the viscous balance equations by I, and adding to the first, we get a second order linear differential equation with a complex coefficient. Looking at the solution to this, we can see that as depth increases, velocity must decay to zero, thus A equals 0. And at the surface, the velocity is the surface velocity. Thus, the velocity can be written like so. Using Euler's formula, we can further rewrite S. We get an exponential decay term that indicates the magnitude of velocity weakening exponentially with depth, and an oscillatory term that indicates the direction of velocity spiraling with depth. Here we define the depth velocity decaying by e to the minus 1 or by a significant amount as the depth of the Ekman layer. Now focusing back on wind stress, at the surface of the water, the wind stress balances the viscous shear stress just below the surface. Using the equation for shear stress in a viscous fluid and substituting in kinematic viscosity, we have take the derivative of S with respect to Z. And then at the surface, this becomes, then equating with the wind stress expression from earlier, rearranging for S0, the term 1 over 1 plus I simplifies to root 2 over 2 e to the minus I pi over 4. So the surface velocity is expressed as The phase term e to the minus pi over 4 shows that the surface velocity is at 45 degrees to the wind direction. The net volume transport in the Ekman layer is calculated by integrating the velocity s of z over depth z. This shows that the net transport is at right angles to the direction of the wind and clockwise in the northern hemisphere. The mass transport is the volume transport multiplied by the fluid density. Putting this lengthy maths all together, we have found a theoretical description of how the Coriolis force, combined with viscous forces, influences the movement of fluid layers, also known as Ekman motion. Let's summarize what we know about its key features: the Ekman spiral and Ekman transport. The Ekman spiral refers to the patterned velocity in a fluid where each successive layer below the surface is deflected relative to the one above it due to the Coriolis effect. In the northern hemisphere, the surface current is deflected 45 degrees clockwise relative to the wind direction, anti-clockwise in the southern hemisphere, and the deflection increases with depth, forming a spiral structure. The spiral continues downwards until the motion is negligible, often at a depth called the Ekman depth. Ekman transport represents the net effect of this motion. Averaging across all layers, the water is transported at 90 degrees to the wind direction, clockwise in the northern hemisphere and anti-clockwise in the southern hemisphere. I hope this was a useful recap of Ekman motion and its significance in ocean dynamics. Thank you for watching.